So here is an interesting visual. It comes from Ward. Ward had an issue in he said 1607, which was called The End of Science. And basically, this issue discussed the point that the big data revolution is changing science. It's not really the end of science, it's just the start of a new science done with a new methodology, which is data-oriented rather than theory-oriented, or more precisely hypothesis-oriented. The traditional way you analyze data was to state an hypothesis, then you asked if that hypothesis was true. This is how you were taught to do experimental science. Now, that's not so obviously what you do. You just look at the data and you don't state a hypothesis, you just see what the data tells you. So that's data-driven science as opposed to hypothesis-driven science. So the end of science here is the end of hypothesis-driven and/or theoretical science. That's of course not, it's not really ended, it's just not the only game in town. So let's discuss this a little bit. So there are now 4 paradigms identified, or paradigms or methodologies of doing scientific research. The traditional ones were theory and experiment, where experiment is driven by hypotheses. And the trivial example is Newton, who looked at apples falling, and that helped him to design his theory of mechanics. Then around 1980, it became clear that there was a third approach to science, which was basically simulation. So this is taking a theory, or often actually, inverted commas, just a model, and you took that theory or model and you used it to simulate what the theory or model predicted for a certain observation. So that's the so-called computational science, or the third paradigm of scientific research. The fourth paradigm, which was identified most clearly by this online book from Microsoft with the URL here, the so-called fourth paradigm book called Data-Intensive Scientific Discovery. That's data-driven paradigm of scientific research. Note this book is free, and it basically, it has what we've said. It has a data-oriented rather than model-oriented view of discovery. So here's an interesting comment, namely around 1990, I said this method 3 became known actually before that, but it became particularly prevalent around 1990 because there was a big initiative started based on its importance to build supercomputers and things like that. And I thought this was pretty important, and I would try to persuade Caltech, a university I was at the time, to actually adopt a so-called computational science curriculum and train people in this area. And I was not successful. They possibly wisely said this was premature and inappropriate. And now we sort of are doing the same thing, but for data science, not for computational science. We can wonder if this is going to succeed or not. Then will data science curricula succeeds? And I just note here that there is a difference between data science and computational science, and that is the number of jobs. The number of jobs, as we've discussed in data science, is pretty large. McKinsey tells us there's 190,000 nerds and 1.5 million more general people needed by 2018. So given the number of jobs, it is reasonably interesting to ask whether we shouldn't directly train people, get people with degrees in data science rather than degrees in physics or chemistry or computer science. Maybe degrees in data science are good. There's an alternative, which is to give people degrees in computer science with a specialization in data, or degrees in physics with a specialization in data. This type of choice is not quite clear, and I do not know how it will emerge, but I think the case for data science is stronger than for computational science, just because of the number of jobs, and that's sort of why maybe you're at this class.